Welcome everyone to the One World Combinatorics Onwards seminar. Our speaker today is Christopher Cabezas, who is at the University de Liège in Belgium, but is at this very moment at the CERM in Marseille. And he's going to speak to us about large normalizers of odometers and ZD automatic sequences.
Well, thank you a lot, Narat, for your introductions. So yes, as Narat said, I'm actually now working as a postdoc researcher at Université de Liège. I'm working with Julien Leroy. And I'm going to talk about a bit of work that I did a little bit after my PhD with my previous supervisor, Samuel Petit, related to large normalizers of odometers and CD automatic sequences. So the idea is first to understand what are the words that are on this on the title. So this is a Combinatorics and Words seminar. So I will explain in this. So to understand this, first I'm going to in this talk consider topological dynamical systems where the action is given by a CD action, like for example the full shift the d-dimensional full shift, or any subshift given by a CD action, where X is a compact matrix space. And in this case, I'm going to say that isomorphism will be an homomorphism between the system and itself, such that there exists an automorphism of CD that acts on with these isomorphisms in the following way. It is kind of similar to where a topological factor or a conjugacy or an automorphism is, but there is a change of the action that when you commute with the real action. So there is this automorphism acting like this, the automorphism of CD. So the idea is that these isomorphisms, in some sense, capture some symmetries that your topological dynamical system or your subshift or your favorite tiling has that doesn't commute with the action. For example, if your tiling has some rotational symmetry, then this rotation will be captured by this type of isomorphisms because the rotations doesn't commute with the action. And also reflections. So this is the types of symmetries that these isomorphisms relate. So when M is the identity, these isomorphisms are no more than the actual automorphisms that automorphisms are basically the homomorphism that commutes with the action. So there is an algebraic way to define them. So in the one-dimensional case, there is already known notion about these isomorphisms that are flip conjugacies. So flip conjugacies are actions that commutes either with the action or with the inverse of the action. And the idea is that the flip conjugacies are an invariant for what is called the orbital equivalence of dynamical systems. And because of these captures of symmetries that are not related to commuting with the action, there is some researchers that call these isomorphisms extended symmetries, especially in the physics world, because in physics world, automorphisms are called symmetries because they reflect symmetries. So these isomorphisms reflect more symmetries than the actual automorphisms. That's why the name. Now, the normalizer will be basically the set of the collection of all of the isomorphisms of a dynamical system. And as a set, is actually a group. And in comparison with the automorphism group will be a normal subgroup of the normalizer group. And the chief action given by the action itself will be also a normal subgroup of the automorphism group. And algebraically speaking, we have this definition of the automorphism group and the normalizer group. The automorphism group is defined as the centralizer of the chief action, where the big group is the whole homomorphism between X and itself. And with this definition, we can define actually the normalizer as the normalizer, and that's what the name of the chief action given by the same big group, the homomorphism of X. So as the automorphism preserves the same, it has the same conjugacy with the action, the isomorphism, the idea is that preserves the shift action when you conjugate with the isomorphism, as for example, rotations. So as a last final definition, we have what is called the linear the linear representation group, or the linear symmetries of the dynamical system, which will be the set of all of the matrices or all of the automorphism of CD that defines at least one isomorphism. So with these groups, we can define actually some exact sequence that project the automorphism group on the linear representation group, where in this exact sequence we have the natural injection, is just the embedding, and the projection of the normalizer group to the linear representation group is when you take an isomorphism, you just give the matrix. I did a presentation I think 2 weeks ago, and when I said that, someone asked me why this is well defined. This is because we are only considered systems that are aperiodic. So when the system is minimal and aperiodic, when you have an isomorphism, the matrix is unique. So this function Y is well defined. So classical questions that involve the study of automorphism groups and now normalizer groups are just typical questions such as what we can say about these groups as groups. Are they abelian? Are they amenable? Can we say something about the subgroups of these groups? So what can we say about the quotients of these groups? And also, when we have this exact sequence, we don't actually know if the automorphism group the normalizer group is the semi-direct product between the automorphism group and the normalizer group. So there is no general criteria to say when this is true. And also, some other questions are, what you can say about the dynamical properties of the system itself imply to the normalizer group as a group itself. Or you can actually ask, for example, what is the action of the normalizer group to the, for example, the invariant measures of the system? This is the classical questions of homomorphism between the dynamical systems. So we try to answer these questions in big classes of dynamical systems, and we started with the constant odometer systems. Now, there is a lot of definitions on how to define an odometer. And in this case, in the multidimensional case, we consider the following. First, we are going to take an expansion matrix, an integer expansion matrix, which is a matrix which is integer, so it has the determinant is not 0. But the norm of the matrix is strictly greater than 1, but also the inverse of the norm of the inverse of the matrix is strictly less than 1. This means that when you apply the matrix to some vector in Rd, except when it's 0, the norm of the application is always strictly greater than the norm of the original vector. This is also equivalent to when you compute the eigenvalues of the expansion matrix, and then you compute the absolute value of these eigenvalues, then the minimum has to be strictly greater than 1. So for example, 2 times the identity, 3 times the identity, but there is more than that. So the idea is that when you consider an integer expansion matrix, since it has integer entries, then when you apply the matrix to CD, you will have a sublattice of CD. And when you consider the iterations of the matrix, you will have more and more bigger lattice, and eventually you will have only the identity. So you can consider the quotient, and since in an expansion, this quotient is finite. And you will consider the inverse limit of this quotient, and is well defined. And is, the odometer you can consider as the sequences of all of the products of these finite quotients, where you can project the sequences from the future to the past. And this odometer is an abelian group. The action is just to sum by coordinate, and it is a Cantor set. And the action, which is just given by the projection of CD, and you just addition the elements, is actually an aperiodic minimal and equicontinuous system. So the odometer systems, as a topological dynamical system itself, are kind of the most basic dynamical system that you can think. It's just a rotation on a compact topological group. So the question is, what can we say about the normalizer group of an odometer system? Sorry. Well, we have an answer for that, and we have a characterization of when a matrix or an automorphism of CD defines an isomorphism on this odometer system. So we have this criteria. I will explain basically what it does, thinking, for example, if the matrix is a rotation. Basically, the criteria that says is that when you consider the lattice of Ln and then you apply the matrix M, then you will have obviously a totally different lattice. And then you want to know if this new lattice is actually embedded in some lattice of some power of the matrix L. And when that's happened, then this matrix defines an isomorphism. And the isomorphism is basically to study like this rotation that this matrix satisfies. And in particular, when the matrix M commutes with some power of the lattice, then it will always define an isomorphism on the odometer defined by the expansion matrix. And this is a characterization that was already proved before by Giordano Puttamasco, where they actually study some types of isomorphisms between odometer systems with a different point of view when they consider the odometer system as sublattices of Q to the D. But the criteria, it was very similar. So using this criteria, we could say a lot about the normalized group of the odometer system. First, recalling that since the odometer system is an equicontinuous system, the automorphism group is conjugate to the odometer system itself. So any element of the odometer system defines an automorphism by addition. And in this case, well, normally in this presentation, I talk about isomorphisms, but you can define as a topological factor only continuous surjections. And in this case, you can also define the linear representation group, but in general, you don't know if it is a group or not. But in this case, it is a group. And in the odometer case, the normalizer group, it is actually isomorphic to a semi-direct product between the automorphism group that, as I said before, is the odometer system, and the linear representation group of the odometer system. So when you want to study what are all of the isomorphisms of an odometer system, we just need to understand what are the matrices that defines an isomorphism, because the other part you already know. So what we got is that the set of matrices, it vary a lot depending on what are the expansion matrices. So for example, if the expansion matrix is the diagonal 2 and 3, then it's just the diagonal matrices. So the linear representation group is isomorphic to the cyclic group of, sorry, it's not cyclic, it's C to C times C to C. But if you have the diagonal 2 and 4, all of the matrices define an isomorphism on the odometer system. We have other cases. For example, this is a triangular, upper triangular matrix with the eigenvalues 6 and 2. And then we have this countable set of matrices that defines an isomorphism, that it is actually conjugate to the upper triangular matrices with the determinant 1. In this case, we have a matrix that has complex eigenvalues, And in this case, the result is that the linear representation group is only the matrices that commute with the original matrix, with the expansion matrix L form. And in this case, it's a finite group, which is isomorphic to the cyclic group of order 6. And when you have irrational eigenvalues of the expansion matrix, then the linear representation group is also only the matrices that commutes with the original expansion matrix. And in this case, it's an infinite group because contains at least this matrix, 2, 1, minus 1, and all of the iteration of this matrix. So in general, for the two-dimensional case, we can actually compute the linear representation group of the odometer system. And the matrices that are inside this linear representation group are the ones that satisfy some explicit relations with the determinant and the trace, or saying in a different way, are the satisfy some explicit relations about the conjugate invariance of the expansion matrix, which is the determinant and the trace. The problem is that our techniques that we developed to study the constant phase C2 odometer system is that they are not very good to be extended for higher dimensions. So for now, we don't know what is the general criteria to say about the linear representation group of higher dimensional odometer systems. So we have these two open questions. Are the elements computable? And is it the group structure also computable? So the idea was to then say something about, okay, so we know about the normalizer group of odometer systems. So we want to now see something about the normalizer group of multidimensional subshifts. The idea was given by the fact that we can actually project the isomorphisms of a subshift to isomorphisms of the odometer system. Because normally, these odometer systems are what is called the maximal equicontinuous factors of some known multidimensional subshifts. For example, in the topless subshift and some other substitutive subshifts. So related to this study, as a general background, we have a finite alphabet. And in this finite alphabet, to the power CD, we consider just the product topology given by the district topology in the alphabet. And in ACD, we have, as always, the chief that just move the elements by the vector C. And a subchief will be just as a subset which is closed and chief invariant of the full shift. So before of this study of the odometer systems and the normalizer group of odometer systems, I studied before how to define a multidimensional substitutive subshift. Now, normally, in the general notion, there is still no general description of what is a multidimensional substitutions. So we consider an analog, a multidimensional analog of the constant length substitutions. Now, to capture the nature of the constant length substitutions, okay, so we have obviously the length of the patterns that define the substitution, but also we have what is called the support of the substitution, that in this case, for any letter, the support is always the same because it's constant length, which is from 0 to L minus 1. Now, what are the properties that we capture of the length, which is L, and the support, which is the set from 0 to L minus 1? Well, L itself defines an endomorphism between C to C. So we capture this property as for the higher dimensions. So to define endomorphisms in CD, we need a matrix, but also we will need that it satisfies this property that eventually you will have only the identity. So that's why we need that the matrix is an expansion matrix. And for the support, normally, what is the set 0 to L minus 1 given by L, the lattice L of C? Well, the set 0 to L minus 1 is a set of the representative classes. So we consider a fundamental domain of the lattice L of CD in CD, which is the set of the representative classes of the quotient CD given by L of CD. And we are always going to assume, to not have problems, that the representative classes of the lattice of L of CD is 0. So 0 is always in this set. So the multidimensional constant shape substitution will be a map from the alphabet to the alphabet to the power f, where f is this fundamental domain. So, for example, people have been working a lot in what is called the square substitutions or rectangular or block substitutions, where the support is a square or a rectangle, but we can do some variations of that. For example, we can modify the square. Instead of taking 1, 1, we take -1, -1, and we get this triangular substitution. Now, this in particular, I call it the triangular tumor substitution because it's 0, 1, 1, 0, and 1 is given by 1, 0, 0, 1. And the triangular form maybe is not seen in this iteration, but when we iterate the substitution, we will see that it is actually a triangle. So, of course, the problem is how to define the iterations. Now, for the original definition, we need two things, the expansion matrix and the fundamental domain, or the support of the substitution. Now, the expansion matrix for the iteration, it shouldn't be so surprised that it should be the iterate the powers of the original expansion matrix. But for the fundamental domain, we will need something that acts well with the substitution. Now, to do this, since the substitutions are basically something that is defined in a recursive way, the supports will also be defined in a recursive way. So to obtain the next fundamental domain, assuming that you have the previous one, you will apply the expansion matrix to your previous fundamental domain. Then you will have a expanded set. And then in each of these points, you will do the sum of the original fundamental domain. And this will give you, actually, is something that you can prove using group theory, a fundamental domain or a set of the representative classes of the quotient of CD given by L of n plus 1 of CD. Something that I didn't mention before is that also using some basic group theory arguments, the cardinality of this fundamental domain is actually the absolute value of the determinant of the expansion matrix. Now, we cannot define substitutions by any type of fundamental domain that we want. For example, if in one-dimensional case, you consider the endomorphism multiplying by 2, it is common to use the support 0, 1. And then you will fill the whole natural integers when you apply the substitution to infinity. But for example, instead of taking 0, 1, you can take 0, 3. Why not? It's a fundamental domain. So when you do this, you can, when you apply the substitutions and define the support in this recursive way, you will obtain only the multiples of 3. So you have 0, 3, 6, 9, blah, blah. So in this particular case, if you define a substitution with this support and this expansion, you will not be able to define a word of length 2 because there is at any part 2 consecutive elements. So to avoid this type of things, we are always going to assume that the sequence of the supports is a Fellner sequence, which means that whenever you take your support and then you move it by a finite vector, then actually you don't, there is no variation of how many points you have in the intersection of this point. So for example, the square substitutions, you have your support of 2 to the power of k to 2 to the power of k, for example. And then when you move it, well, the intersection is still something around 2 to the power of k. And the border is around something, sorry, 2 to the k square. And the border is something around 2 to the power of k. So at the quotient, it will go to 0. So in this case, it's a Fellner sequence. And for example, in this particular triangular support, maybe cannot be seen, but it's also a Fellner sequence. And the iterations look like this. So first we have this iteration of the red one, yes. And then the second iteration will look like this. And then the third iteration will look like this. Maybe it's still not seen that it's a Fellner sequence, but someone mentioned that, for example, when I present this 2 weeks ago, here you will have some in this. I don't know if my mouse is seen in the screen, but in this part there is something that is being enclosed by in this image 3x3 square, and then eventually it will be a bigger and bigger square. And this is some argument to say that it is a Fellner sequence. I didn't put on these slides, but recently with Julien Leroy, we proved actually that to evaluate to check whether these fundamental domains are actually a Fellner sequence is decidable. That was a question that I did since my PhD. So we can decide whether these things satisfy this or not. Now, the hypothesis of being Fellner not only help us to define supports of words with sort of, patterns of supports arbitrarily large, but also it helps us to prove a lot of properties that the substitutions already has in the one-dimensional case. For example, for the proof of that the substituted subchief is uniquely ergodic, you need that the support is a Fellner sequence to study the ergodic theorem, the ergodic average theorem. Now, what is the substituted subchief? Well, is as in the one-dimensional case, is the collection of all of these elements of A to the power CD, such that any of the patterns that occur in this element, it is produced by the substitution. So it is it occurs in some iteration of some element of the substitution. And also some definitions that we derive from the one-dimensional case. We say that the substituted subchief is primitive if there exists some iteration of the substitution, such that when you take any pair of letters, one letter occurs in the patterns of the second letter. The primitivity assumption is given by the fact that when you have the substitution is primitive, then your substituted subchief is actually minimal. And then we say that the substitution is aperiodic if any point of the point is aperiodic. So there is no period on the set. So what we would like is aperiodic and minimal subchief. So for example, primitive aperiodic and primitive substitution satisfy these properties. Now, to study the normalizer group of subchief, we have this seminal theorem of proved by Curtis, Hedron, and Lindon, that originally it was proved for the one-dimensional case, but we can do some variations to actually prove this type of things. So when you consider an isomorphism of a subchief, so we have this almost commutation with the action, but you have the matrix M acting on the action, sorry. Then the isomorphism group is given by a sliding block code, so or a cellular automaton. The only difference of this matrix M is that the window that the center of the window that you need to consider to compute for example, the coordinate C of phi of x is that it is not C, is m-1 of C. So since you have at most countable sliding block codes and you have at most a countable set of matrices, the normalizer group of a subchief is always a countable set and a discrete set on the set of homeomorphism of X, as for the automorphism group in the classical way. Now, before our study of the normalizer of the odometer system, are also for the subchief that I'm going to mention later, there has been some studies implying that the normalizer group was finite for, sorry, the linear representation group was finite for a lot of substitutions. For example, we have the work of Michael Backe, Roberts, and Rinjasawi, who studied the normalizer group of the chair tiling and the Lerapier chief, but the Lerapier chief is a chief of finite type, but it's not a substitutive subchief, but it's still finite. Then we have the work of Álvaro Bustos, who studied the normalizer group of the Robinson tiling. And he proved that the matrices that defines isomorphism on the Robinson tiling was only the symmetries of the square. Then we have the work of Álvaro Bustos, Daniel Luz, and Neil Manivo, who studied the normalizer of some bijective block substitutions. And they also proved that it was only that the matrices that basically permutes the excess of CD. And then there was a study that I did of the normalizer group for some extremely permutative substitutions, which is a definition that basically asks that when you see the support of the substitutions, and you see for any letter, there is some elements of the fundamental domain where the substitution is bijective. It's not completely bijective in the whole set. It is bijective in some parts of the substitution, and in this part is given by the extreme points of the convex hull of the support. I'm not gonna talk more about this, maybe if you have questions later, but it was also a finite set. And there was some other studies where they get some subchief that has infinite linear representation group. For example, the normalizer group of the full shift. In the full shift, for any matrices, you have an isomorphism. And there is a study of Michael Backe, Álvaro Bustos, Hook, Lemanchik, and Nickel that studied the normalizer group of some number theoretic positive entropy chief. And they also got a lot of chief that has that the whole matrices define an isomorphism. So in this last study, sorry, I forgot about this. So for example, we have the table tiling. So the table tiling is defined by two rectangles. One is horizontal and one is vertical. And this is an image of how the table tiling looks when you iterate the substitution tiling. And there is a way to obtain a conjugate substitution for the table tiling. And the idea is that you code what are the squares that define this substitution. Now, this substitution is a bijective substitution. If you put the focus on one coordinate, for example, in this 0, 0, you have all of the letters, and then this property will satisfy in all of the coordinates. So it is a bijective substitution. So by the results for the previous result, we know that the normalizer group is the linear representation group is finite. So we actually compute what is the linear representation group of this chief, and is the symmetries of the square. Now, as I said before, the study of Backe, Bustos, Hook, Lemanchik, and Nickel asked whether all of the substitutions actually satisfy this property of finiteness of the linear representation group. And the answer is no. So with Samuel Petit, we prove actually that for any dimension, there exists a periodic primitive constant shape substitution such that the linear representation group of this particular subchief is the whole GLDC. So any matrix, any isomorphism of CD defines an isomorphism of the group. So this is one of the first examples known of zero entropy minimal subchiefs satisfying this property. And something that shows is that the normalizer group is not even amenable for this type of chiefs. Now, normally the substitutive subchiefs are set that are subchief of low complexity. In the one-dimensional case, they have most square quadratic complexity, but they are not minimal. And if you consider minimal, they have only sublinear complexity. And in this case, it has some, in the multidimensional case, something that with Julien proved very recently is that this substitution has polynomial complexity depending of the expansion matrix. So they are low complexity subshifts. Something that is also intrinsic in this thing is that normally substitutions are the most basic example that you can think of subshifts. So normally all of the properties that these substitutions has are that they are finite in some sense. So this linear representation group is kind of the first infinite thing, infinite invariant thing that substitutions satisfy. Now, the example for the two-dimensional case is inspired by what is called the half-X tiling. So the half-X tiling is given by this, the half of an X, and is inflated by 2. And then the inflation is subdivided by some rotations of this original half-X. Now, to take in the centers of the half-X, we can prove that the action given by the centers of this lattice in R2 are conjugate to this particular constant shape substitution. What is the property that combinatorially this substitution has? In 0, 0 is bijective. So 0 goes to 0, 1 goes to 1, 2 goes to 2. And in any other coordinate is equal in all of the supports, in all of the image of the substitution. Now, this substitution is actually, because of this property, since it has a coincidence, it actually has a lot of coincidence. A coincidence is a point where all of the images is the same. This defines a multidimensional Topliss subshift. And since it is a Topliss subshift, we have some properties derived by being a Topliss subshift. For example, there exists almost one-to-one factor from the substitutive half-X to the odometer system defined by the expansion matrix that is, 2 times the identity. And there is an injective homomorphism from the normalizer group to the normalizer of the odometer system. Now, in this particular case, the odometer system given by 2 times the identity is given by the whole GL2C. So it was the good odometer system to have the largest possible or normalizer group for a substitutive subshift. And in this case, the normalizer, the linear representation group of the substitutive subshift is included on the linear representation group of this normalizer, of this odometer. So we have this property. And the idea to prove that it was actually the whole GL2C is given by the fact that the half-X tiling satisfy a good automatic property. So it defines a two-dimensional automatic sequence. The property that satisfies is the following. We can define a map from the whole C2 minus 0 to the support F1 minus 0, given by the following way. We compute, we take a vector and we compute what is the first time that it is not contained on the lattices given by 2 times the identity. So for example, if you have a vector which is even in the first coordinate and odd in the second coordinate, then it is not on the lattice given by 2 times the identity. So you compute what is the residues divided by 2. So since it was even in the first coordinates, the residues will be 0. And in the second coordinate, you have an odd integer, so it will be 1. So in this case, for this vector, the fixed point of the half-X will be given by the coordinate in the substitution that it is the 0, 1. So in this case is 0. So for any element that is even odd, in the fixed point, you have 0 in this coordinate. And this is satisfied for any point in the whole C2 minus 0. And the important part is that when you take any matrix M given in GL2C, this matrix M commutes in this case with this function. So given by this fact, we can define an isomorphism by any matrix that is defined by the Corti-Scaglione theorem on this way, and we can prove that it actually defines an isomorphism on the half-x substitutive subject. Now, other properties that the half-x substitutive subject satisfy is that the automorphism group is trivial, is only the chief action, and the normalizer group is the semi-direct product of C2, which is the chief action, and GL2C. Now, in general, we have a way to compute for any expansion matrix a substitutive subchief that satisfy a property very similar to this part. So it defines automatic sequences for any expansion matrix that satisfies these 4 properties. The first one is that is coalescent, which means that any endomorphism or any topological factor from the substitutive subchief to itself is invertible, so it is an automorphism. And actually, the automorphism is just the chief action. So these self-conjugacy are just the chief. And the linear representation group is very similar to the one that defines the odometer system defined by the expansion matrix. But there exists this stabilization property that the expansion matrix need to have in order to define a matrix, an isomorphism to the substitutive subject. For example, for the expansion matrix 2004, so the diagonal 24, I mentioned before that the linear representation group of the odometer defined by this matrix is equal to GL2C. So all of the matrices in the odometer satisfy define an isomorphism on the odometer system. But for this particular substitutive subchief that we can define with this expansion matrix, since we have this stabilization property that the matrix need to satisfy, for this particular case, the matrices are the upper triangular matrix where the diagonal is R1s or -1 to have determinant 1. And on the non-zero element are multiples of 4. So they are not equal to GL2C. And always these substitutive subchiefs satisfy that the normalizer group is actually a semi-direct product of the chief action and the linear representation group. And the isomorphisms are explicit, are just this type of isomorphism given by this definition, and the rest is only chiefs. So the question that is still open is if we can actually compute the linear representation group of any substitution, and we can we say something about the group of structure of this linear representation group. Thank you for listening.
Thank you very much. Sorry, my video is not starting. Does anyone have any questions? So that triangular 2A Morse substitution, was it you who introduced this substitution, or had it been previously studied before?
Okay, that's a good question. I think that the idea of constant shape substitutions was introduced by me, but the notion of studying weird supports is not given by me. It was actually, I think that the first time that someone studied this taking weird fundamental domains was on the 90s. for example, is one given by, there is an article of Andrew Vince, who studies some properties of these fundamental domains. I think that he took in a very general context for not only fundamental domains. He took some sets and he computed what happened when you iterated in this way, what you can say on for these things. There is also some studies later who study something called the digit tile. The digit tile is given by the following fact: since this is an expansion, the inverse is a contraction. And you can actually define a contraction given by the inverse of the matrix and the support. And someone studied, for example, the convex hull of this digit tile. And I actually use these studies of the convex hull when I mention this work of the normalizer group of extremely permutative substitution. And using these definitions, I think that I was the one who introduced the constant shape substitutions. We using these definitions.
Okay, great. Thank you. Does anyone else have a question for Christopher? If not, thank you so much for speaking in the seminar.
Thank you.